You are watching the 4.5 lesson video on comparing linear and exponential functions. So we actually, at the beginning of this unit, started talking about linear and exponential functions, or we stopped talking about linear and then started talking about the similarities and differences between the two of them. So what we're going to do today is just summarize and just look at things a little bit in depth, but nothing really is going to be new today, which is good. All right, so exercise number 1. There's two tables. One is going to be a linear and one is going to be exponential, and which is which. All right, so in order to determine which is which, first we're going to notice similarities and differences. I notice that all my x values are the same in both. So 0, 1, 2, 3, 4, they're both constantly increasing at the same rate. Let's check out the y's. All right, 5, 10, 20, 40, 80. What's happening there? Well, if I add 5, then I'd end up with 15, and so that's not it. So what's another way that I can get from 5 to 10? Yeah, multiply by 2. Is this true? Is 10 times 2 20? Yes. Is 20 times 2 40? Yes. Is 40 times 2 80? Yes. Okay. So that has a multiplier. So what do we know? Yes, this is exponential. And then how you know, or how we arrived at our answer, because it says we need to explain. We know this because it has a multiplier of 2. Sorry, that took a lot of space. All right, we're going to have to squeeze this one in over here. All right, well, at least we know table 2 is linear. So let's figure out what's going on. How do I get from 8 to 11? That's right, add 3. What if I add 3 here? Yep, that's going to work. What if I add 3 to my y's? Yeah. So how do we know that this is linear? Well, we have a couple ways that we could describe it. You could say it has a constant rate of change. It has a number that's being added every single time. I'm going to say it has a constant rate of change, aka slope. Okay, moving on. So find equations in standard form for each of the two functions. All right, well, I like this. I can do this. We have a starting point for each of my functions. So table 1 is going to be y equals, well, the y starts at 5, and then every single time it's multiplied by 2 over and over and over again. So we're going to model that repeated multiplication with, you got it, that exponent. Table number 2, we start off with the y, we begin with 8, but what we're doing this time is adding 3 over and over and over again, and we show multiplication when we want to model repeated addition. So those are our two equations. All right, exercise 3. Consider these 2 points, 0, 12, and 1, 3. Okay, so what does it want us to do? It wants us to create a linear equation, and then it wants us to create an exponential equation. Oh, this is interesting. Okay, so I guess I'm going to divide this up into 2 parts. This is going to be linear, my linear side, and this is going to be my exponential side. This is kind of cool. Well, okay, they gave us what? They gave us 2 points, right? They gave us the points 0, 12, and 1, 3. Well, when we're dealing with a linear function, we're always looking for something that's being added or subtracted. So let's go ahead and figure out that piece. How do I get from 12 to 3? Well, what did I have to do? I subtracted 9. And how did I get from 0 to 1? Well, that was easy. I just added 1. So my slope, or my rate of change here, is just -9. So if I want to come up with an equation, I'm going to have y equaling my initial value of 12, right? We have that y-intercept hanging out on the table nicely. They gave that to us. And then what are we doing every single time? Well, we are subtracting 9x. All right, exponential. Well, we still have the same 2 points, right? But I got to figure out how we got from 12 to 3 using multiplication. And some of you might say, well, isn't it division by 4? 12 divided by 4 is 3. But what's another way to write dividing by 4 if I need to use multiplication? Yes, we are going to multiply by 1/4. So, writing my equation, y is going to equal my initial value. We're still starting with that 12, but only this time we're going to multiply it by 1/4 over and over and over and over again because we need to define the multiplier again because I was looking at the exponential. Here I was looking at linear, so I had to do adding and subtracting. But let's not forget repeated multiplication is in terms of an exponent. So 12 times 1/4 to the x power. All right, let's jump over to our calculator, and I'm going to pause the video, graph these two on the same graph, and it tells me what window to use for my x's and y's, so make sure that you do the same. All right, so here you can see the two beautiful graphs that we created. One thing that I noticed when I went to graph it over on our paper is that when I graphed, I actually had my point wrong, so I fixed that. So make sure it's the 0.13. I think I had 0.53. So Mrs. Ruscio, be careful of your scale. Okay, I'll make sure to do that the next time, but I fixed it for all of you, and I labeled both graphs. Another thing, if we look at the table by putting Control T, we can see that the 0.13 and the 0.012 are in both of the columns, which means that we found both equations correctly. Yay! All right, exercise 4. Typical Regents question. It's saying which situation is not a linear function. So linear, remember, we're going to have an add or subtracting value every single time. As soon as we see that, then bye, because that would be linear, and we're looking for one that's not. So number 1, a gym charges a membership. I can't talk today. I am so sorry. I'm not re-recording this video. It's a membership fee of $10 down and $10 per month. So we're going to pay $10 initially, and then every month, $10 added on, plus 10. Not you. Okay, cab company charges $2.50 initially. That's a y-intercept. And then $3 per mile. So we're adding $3 per mile. This case, it was $10 per month. Okay, so that's not it. Number 2 is not it. Uh-oh. Okay, number 3, a restaurant employee earns $12.50 per hour. Yep, we're adding $12.50 per hour. That's an adding fee. All right, and then 4, well, let's hope this is not linear. A $12,000 car depreciates 15%. There's our multiplier. So what in this case, if we want to really snazz this up, this would be multiplying by 0.85 every year. And where did I get that 0.885 from? Well, that's just 100% minus the 15% depreciation, which is 85%. So our winner here is number 4. Okay, exercise number 5. Here we go, rock and roll. We have 2 functions. We have a linear function and we have an exponential function on the right. Okay, what is my y-intercept for my linear? Well, this is, I don't even think I need a calculator for this. It starts at 5, right? There's my initial value, and then we're adding 20 every single time. So 25, 45, 65, 85, 105. Did I do that right? Yeah, 2 times 3, 60 plus 5. Yeah, okay, cool. All right, now with the second exponential function, we're still starting at 5, but I actually now have a multiplier. So just so I can show my work a little bit, I was adding 20. Here I'm going to be multiplying by 2, because that's what my base told me to do. Here I was adding 20 every single time. So if I finish the rest of the table, what is that? 10, 20, 40, 80, 160. All right, easy. Didn't even have to use my calculator. Loving it. All right, so part B says graph and label each function. Each function, okay, we got to do both of them. And then we need to do it over the domain. Wait a minute, we have two different graphs here. So one of them we're going to graph from 0 to 3, and this one we're going to graph from 0 to 5. All right, I'm going to pause the video. I want you to graph, and I'm going to reconvene in just a moment. Okay, so here you can see my two beautifully labeled functions on each of the different domains. Notice how I don't have arrows because it restricted both the domains. The moral of the story is here, always look at the window. It can be very deceiving if you only look at small snapshots. Like if you look at B, it looks like, I don't know, y equals 5 times 2 to the x. The exponential may never ever catch up to the linear function, which in the second case, it most certainly does and surpasses it in just 2 more moves of our x value. So take a look at the window. Whenever you're stuck, always change the window just to get a better picture of your function.